Es que como a mí no me gusta Marvel ni Star Wars.
Okay, so coming back to the subject, this is going to be the last topic that we're going to see here in the unit. Again, as I mentioned, yes.
Resistor on the no?
You can see it. Where on sorry?
The title of the slide.
Oh, sorry about that. Let me move this. The thing about the zoom slider here.
How do you pronounce the truckers?
Yeah, that's
It's car.
the topic right now is it's called Kirchhoff's law.
Where is he from?
I'm not sure. I'm really not sure. I'm imagining he's probably German or Swiss German or something like that. So basically, when we're talking about electrical circuits, there are certain basic laws and things that apply to every electrical circuit that are kind of like the Bible, the guidelines for electrical circuits that anybody that works in electrical circuits should know. So one we've already talked about, which is Ohm's law, that has to do with the relationship with the voltage, current, and resistance. And the other laws that govern electrical circuits are called Kirchhoff's laws. Now, remember that when you're working with, I don't know, a dynamics problem or a statics problem. Well, what are the laws that you use? We obviously use Newton's laws. Those are the basics. Well, we're going to use Newton's laws. And Newton's laws are going to help you analyze and determine. So every area of physics are going to have their basic laws. Kirchhoff's laws are going to be laws that are going to govern electrical circuits. They're very simple to understand. Basically, Kirchhoff's laws are based on the law of conservation of energy. So the law of conservation of energy is that basically says that anything that I give, something has to receive it. And anything that's received is because something is giving it. Okay. So remember that we talked about active elements and passive elements. An active element, there's going to be questions in the exam. What's an example of an active element? A battery, a power supply, a generator, anything that provides electrical energy. Those are active elements. A passive element is anything that's going to receive that energy. So examples of passive elements that we've seen up to this point. A resistor, one, correct. A capacitor is also a passive element. Those are going to receive the energy. And there's basically three things that we're going to be talking about here. And those come back to Ohm's law. It's voltage, current, and resistance. Those are the only three things that we're talking about throughout everything. And so, if we have a circuit and we talk about voltage, if I have a power supply that's giving voltage, that voltage has somehow to be distributed in the circuit. If I have voltage and it's a circuit, then that means that there's electrical current being provided. The electrical current has to flow. And so whatever is flowing in one direction and gets to one point has to come out the other direction. Okay. So basically how the laws work. So before we get into specifically talking about the laws, let's talk about some terminology having to do with electrical circuits. Okay. So an electrical circuit. What is an electrical circuit as a definition, or a circuit? A circuit is going to be a closed loop conducting path where an electrical current can flow. The key to that definition is closed loop path. So it means that it has to start somewhere, it has to go around and end at the same point. That's the only way I can have flow. The definition of a circuit is a closed loop conducting path where I have electricity. That's a circuit. So imagine that we have, we also use circuits to talk about like racing, like a racing circuit, right? And a racing circuit is a loop. Would you guys agree? What if suddenly the racing circuit, instead of being a loop, suddenly part of the track just goes wherever? The race is never going to end. It has to be a loop. That's why it's called a circuit. It begins one place, flows, and ends in the same place. That's a circuit. Okay. Are we okay up to this point? So any closed loop where current can flow, and actually an exercise you can do is just put your finger in one place and just move it around. And if you can get to the same place again, that's a circuit. Okay. So you've heard of the term closed circuit TV, for example. What's a closed circuit TV? It's a TV that's here in the classroom that's being monitored or sent to a station that monitors the same classroom. What's an open circuit? An open circuit is any part of the circuit that has been literally opened or cut open where the electrical current cannot flow in. And you guys have probably heard the term short circuit. And short circuit is bad. If I have a short circuit in something, a short circuit is bad. The term short circuit is literally what it means. If I say that a circuit is a closed loop path where current flows, a short circuit is a very, very, very small path. Okay? It's a very small path. Imagine that I have, instead of a very long racing, imagine that you're playing Mario Kart. Okay. And it's a long track. Now imagine that instead of making it a long track, I make it a very small. Like the baby one. Yeah. But a literally very small. Yeah, there is one, right?
No, maybe one that you go on like 8 laps.
It's very small. What's the problem with having a very, very short circuit? Boring. Well, no, yes. Somebody said too fast or something like that. Yes. The problem is that in a short circuit, if I'm going from point A to point B, I'm doing a path. But if it's a short circuit, I'm going from point A to point B, point A to point B, point A. I'm doing it very quickly. The problem with current, and this is something that you guys should remember, current is the movement of electrons, of charges, remember? Movement generates heat. Heat generates movement. Movement generates heat, heat generates movement. And so if I have a very short circuit, suddenly the very fast movement of those electrons is going to generate heat. That's going to make the electrons want to go faster. And when they go faster, there's going to be more heat that's going to want to make them go faster. That's going to be more heat until the whatever material can't support that. That's why it's called a short circuit. Never do this at home, kids. But let's say that I grab a paper clip as a youth, and I put it in the middle of the two connectors in the socket. What am I creating with the clip? I'm creating a short circuit. And if I do that, I'm probably going to get electrocuted, and the lights are going to go up because everything is going to pop. Okay. Suddenly, let's say that I have electrical wires that are moving in the wind, and suddenly the electrical wires touch. The moment they touch, they're generating a very short circuit, and that makes everything blow up. By the way, the relationship that I just said, that speed generates heat generates speed, happens extremely quickly. So the short circuit isn't something that's going to take a long time. The moment it happens, the material is probably going to, depending on the material, is probably going to be destroyed, or the heat is going to generate the material to burn it. Okay, so that's the concept of a circuit. What is a path? Okay, a path is going to be a single line that connects elements or sources. So, for example, I have this power supply here, and then I've got resistor 1. The power supply is connected to resistor 1. That is a path. A path is a connection between elements. Okay? For example, and paths can generate nodes. Imagine that you're walking through a road and suddenly you have an intersection to go right or go left. I'm walking along the path and suddenly I got to a point where the path separates. That point where the path separates into many paths is called a node in electrical circuits. So it's called a node or a junction. And what happens in a junction? Well, there's more than one path I can go. Those are called nodes. So for example, here in the circuit, the nodes are marked. They're in green. Exactly. Like the freeway, you're gonna have different options to go through in the exit. So that's an example of a node where more than one part of the freeway separates. A branch is going to be whatever is connected between two nodes. So notice one thing. If there is nothing connected between two nodes, then it means that they aren't two nodes. It's the same one. For it to be a node, there has to be something in the middle. Okay. A loop is going to be a closed path in which no circuit element or node is encountered more than once. So it's kind of like doing a maze. You can do it here. Let me see if I can draw it. I'm not going to bring out the tablet, so this is going to be ugly drawing with the mouse. Okay. So this is a loop. I'm going to start here. I'm going to go around, and I'm going to end up here. That's a loop. Okay. It's this closed path between a series of elements. What's another example of a loop? This is a loop as well. Okay. This is a loop as well. Those are two examples of loops. Another example of a loop, for example, I'm going to try to paint that in different colors. For example, this is also a loop. This is also a loop.
And the whole circuit.
Correct. The whole circuit is also a loop. This whole thing is a loop. So a circuit can have many loops within it. Okay. A circuit can have many loops within it. This other one is also a loop. This one here, this is also a loop. So a loop is going to be this connection between various elements. Okay? Now, what is a mesh? A mesh is going to be a loop that doesn't have any loops within it. Okay, so a mesh is going to be a loop that doesn't have any loops within it. So, for example, you said, noted, well, the whole circuit is a loop. That's correct, but it's not a mesh because it's got loops inside it. The red ones that I drew, those are meshes. Okay. Because the red ones, 1, 2, 3. Well, this one's purple. They're independent. They don't have any loops inside them. Okay, those are called meshes. It's always confusing sometimes the term mesh and meshes. Right? Okay, questions? Okay. So the pizza thing, is that an individual thing, or can you do something as a group? I know, but is the submission has to be individual, or can you do a picture as a group doing a lot of things with your backpacks? Do you know? I mean, you can.
Like if the grading is individual or by classroom is what you're asking.
No, it's actually, I was thinking that you've got 2 hieleras, an asador, a fryer. You could actually simulate like you're doing a carne asada, but with books and stuff. With
If I took a picture of me Related paper.
Yeah, so that could be an interesting picture there. Okay. Okay. So let's talk about Kirchhoff's two laws and then we'll break. So we've got Kirchhoff's two laws. The first law is very, very simple, and it's the law that everything that comes in has to go out. Anything that goes in has to go out. That's very simple. And what Kirchhoff's first law says, or Kirchhoff's current law, it's called Kirchhoff's first law, or KCL, which is Kirchhoff's current law, says that if I have a node, if I have currents going into the node, the sum of the currents going in has to be equal to the sum of the currents going out. That makes sense, right? Anything that goes in has to go out. Anything that goes in has to go out. Imagine a river. Again, imagine the river analogy. And the river has an intersection. So there's one river, and then the river separates in two. The amount of water that's going in to the intersection has to be equal to the sum of the water that's going to the two paths. Because the water should be conserved. Same thing happens here. Whatever goes into a node has to go out of the node. If we're talking about conservation, this is the law of conservation of charge. In reality, by the way, there might be some loss of current due to some heating characteristics of certain elements that can make current go down or diminish. But even in those cases, the current that goes into a node has to be equal to the current that goes out of the node. And there's two ways to interpret this law. If we're going to write it down as an equation, you can say the sum of the currents that are going in are equal to the sum of the currents going out. That's one way to write it mathematically. The other way to write it mathematically is for you to say what's going in is positive, what's going out is negative. And you say the sum of the positives, the algebraic sum of everything has to be equal to 0. By the way, notice that I just said something. You can say that what's going in is positive, what's going out is negative. That depends totally on you. You can say it the other way around. It's still valid. What's going in is negative, what's going out is positive. The mathematical representation is still the same. The thing with an electrical circuit is that whatever convention I define, I have to do it for the whole circuit. So I can't say for this node, what's going in is positive and what's going out is negative. But for the other node, I'm going to do it the other way around. You have to be congruent in the analysis of the whole circuit. Okay. Questions with Kirchhoff's first law? No. A to the C to the L. Okay. The second law, or Kirchhoff's second law, has to do with voltage. In the case of Kirchhoff's second law, the first law had to do with voltage. The second law is going to have to do with I'm sorry. The first law had to do with current. The second law is going to have to do with voltage. So what's happening here is that in Kirchhoff's second law, the sum of the voltages along the loop has to be equal to 0. Or stated the other way around, or there's two ways to state this, similar to the current, is that the amount of voltage that's provided or the active voltage elements, the sum of those have to be equal to the sum of the passive elements. And so these are also called, in some literature, you're going to find them as voltage drops. They're called voltage drops. So if I have a loop, for example, this loop has 4 elements. That's a loop within a circuit. If I calculate the voltage of each of these elements, the algebraic sum of those voltages has to be equal to 0. So some voltages are going to be positive, some voltages are going to be negative. Everything has to balance itself out or be proportional. This law is called the law of the conservation of energy. The law of conservation of energy. So the first law that was current was the conservation of charge. The second law was the conservation, which has to do with voltage, is the conservation of energy.
And this one, conservation of what?
The first one, which is Kirchhoff's current law, or KCL, is a law of conservation of charge.
Huh?
This one, which is Kirchhoff's voltage law, is the law of conservation of energy.
Wait, this one's the conservation of energy, not voltage?
Yes.
Oh, okay.
All of it is written on
The
the
first one is the KC, the C for what?
current. C is going to be current, B is going to be voltage.
Because although this is voltage, where is it energy then?
It's just called the law of conservation of energy. Because when we refer, usually when we refer to power sources, we refer to them with regards to their voltage. So all of these have voltages, the voltage that's provided. Imagine the power source is providing energy. So the energy that's provided has to be equal to the energy that's absorbed. So that's why it's related to voltage.